Assalamualaikum and a very good morning. Today I would like to teach you about the root locus, which is in the chapter number 5. Okay, as an introduction, root locus is a graphic technique that gives us the qualitative description of the control system performance and also a powerful quantitative tool. The root locus can be used to solve control problems for higher order system. And the root locus can be used to qualitatively describe the performance of a system as various parameters are changed. The root locus can also be used to assess the stability, like the Routh-Hurwitz criterion. Okay, this figure shows the block diagram of the closed-loop system given a forward-loop transfer function KGS, where K is the root locus gain, and the corresponding closed-loop transfer function is given by C of S over R of S equals to KGS over 1 plus KGS. The root locus is basically the set of paths traced by the root of a characteristic equation 1 plus KGS equals to 0. Okay, so in this topic, we actually focus on the characteristic equation 1 plus KGS equals to 0. So this path consists of infinite number of roots as K varies from 0 to infinity. Okay, so here basically we will learn on how to draw the root locus path. Okay, and for the basic one, you can draw it by finding infinite number of roots, okay, to develop the path, as K varies from 0 to infinity. Okay, next I will explain to you on how to draw the root locus. So there are specific procedure to draw the root locus. Okay, first we go to the step number 1. Determine the open loop poles and zeros of open loop transfer function and plot them in S-plane. Okay, as we all know, first we start with the characteristic equation 1 plus kgs h of s. Okay, kg of s h of s equals to 0. So the open loop transfer function is given by k g of s h of s. Sometimes h of s is equals to 1. Okay, so we just focus on the open loop transfer function, then we find the poles and also the zeros. So in this slide also it shows the location of the zeros and the location of poles on the S-plane. Okay, so I hope you still remember on how to draw the zero and poles. So 0 is denoted by the circle, and the poles is denoted by X. Step number 2 is starting and end points. Okay, the root locus starts from the open loop poles, or K equals to 0 points, and terminates on either finite or infinite open loop zeros, or K equals to infinity points. Okay, so that is step number 2. So please remember, poles is K equals to 0 point, zeros is K equals to infinity points. Okay, step number 3 is a number of branch of a root locus. Okay, the number of branch of the root locus equal to the number of roots of the characteristic equation, or the number of open loop poles n. Okay, so I will show you a detail after this. Okay, step number 4 is a determination of a direction of root locus on real axis. Okay, a branch of root locus lies on the real axis if the total number of open loop poles and zeros to the right of the point is odd. Okay, for example, it's like this. Okay, for point number 1, let's say I choose a point number 1 and looks to the right. and I see the total number of poles and zeros are 3, okay, which is odd. So a branch can be drawn through this point. Okay, so I can draw the branch given by this yellow color or yellow arrow. Okay. Next, we go the next point, which is point number 2. And next, I look to the right and find the total number of poles and zero, which are 2. Okay, this is even. So a branch cannot be drawn through this point. Next, proceed for point number 3. Okay, and looks to the right. The total number of poles and zeros are 1, which is odd. So a branch can be drawn through this point. Okay, so that is basically a method to determine a direction of root locus path on the real axis. Step number 5 is a breakaway and break-in points. When two branches move towards or outwards each other on the real axis, coincident point is called a breakaway or break-in points. Okay, this is shown in these figures. Okay, so on the left side of the S-plane, we have the example of a breakaway point. Okay, on the right side of the S-plane, we have example of break-in point. Okay, so normally break-in happen when we have 2 zeros on the real axis. Breakaway happen when we have 2 poles on the real axis. Okay, so how to find this breakaway or break-in point is using the roots of dk over ds equals to 0. So dk over ds can be found from the characteristic equation 1 plus kg of s, h of s equals to 0. Okay, so if you can find this root, it is the breakaway or the break-in point. Step number 6, determine the asymptotes. Okay, for higher values of k, the direction of root locus branch is guided by the asymptote. Okay, so how to find? There are 2 parameters basically. The first one is angle of asymptotes given by the formula theta q equals to 2q plus 1 in the bracket multiplied with pi divided by n minus m. So what is n? N is the number of poles, m is the number of zeros. Okay, so q is equals to 0, 1, 2 until the modulus of n minus m minus 1. Okay, the second terms that you need to consider is the intersection of asymptote with the real axis, which is given by the formula sigma 1. Okay, so sigma 1 is equals to the total number of poles of gs h of s minus total number of zeros of g of s h of s divided by n minus m. Okay, so this is the formula to find sigma 1. Some books call this sigma 1 is a centroid. Okay, centroid point. Okay, I will show you a detail on later on how to find this sigma 1. Step number 7, find the points where the root locus cross the imaginary axis, if any. Okay, some problem they cross the imaginary axis. Some problem they do not cross the imaginary axis. So that's why I put if any. Okay, there are 2 methods basically. The first method is by substitute the s equals to j omega in the characteristic equation and make real and imaginary part to 0. Okay, make real and imaginary part to 0. Then you just focus on the imaginary part and solve for k and j omega. The step number 2, okay, the alternative step, is by using the Root Locus criterion to obtain the value of k and j omega. Okay, so you can refresh back chapter number 4 on the Root Locus criterion. Step number 8, determine the angle of departure or the angle of arrival, okay, of the root locus from the complex poles or zeros, if any. Okay, so departure or arrival is depend whether we have a complex poles or complex zeros. So there are two formulas according to the pole and also according to the zero. So departure angle for complex pole is given by this phi subscript departure equals to 180 degree minus phi of subscript p minus phi subscript z. So phi subscript p is a sum of angle of other poles. Phi subscript z is sum of angle of all zeros. Okay, so please be careful on this formula. All right, because phi of p is sum of angle of other poles, not all poles. Okay, other poles. But phi of z here is sum of angle of all zeros. Next, we go for the arrival angle for complex zero is given by phi subscript arrival equals to minus 180 plus in the bracket phi p. Now sum of angle of all poles, okay, that is phi p, minus phi z, sum of angle of other zeros. Okay, so the detail on how to apply this equation will be shown later at the end of this presentation. Next, step number 9, determine the value of the gain k at any specific root location or point. Okay, so basically the gain k can be determined by using this equation. Okay, this is in terms of sentence equation where k equals to product of length of vectors drawn from the poles to the specific point over product of length of vectors drawn from the zeros to the specific point, or it can be expressed mathematically as shown in this equation. Okay, so that is the end of the procedure. So actually we have 9 steps. Okay, now I just like to explain about what fact that you can find from this root locus. The first one is that the distance of root from the origin of S-plane is equal to the natural frequency omega n of the system at the certain gain k. Okay. Number 2, if a straight line is drawn from the origin to any points on the root locus, this line will create an angle theta from the real axis. Hence, the damping ratio is equal to the cos of this theta. Okay, you can try this. Number 3, the real part of the complex roots distant from imaginary axis is equal to the damping factor of the system zeta omega n. Okay, so this one also you can try. Okay, you maybe can try it for the simple second order system. Okay, next as an example, okay, sketch a root locus for the system with the characteristic equation as shown below. Okay, as multiply with in the bracket s plus 2 multiply s plus 3 plus k equals to 0. Okay, as a solution, I already give you a QR code, okay, which is basically a complete video on how to solve or on how to sketch this root locus. So I hope this video can help you to understand the procedure to draw this root locus in a very detailed. Okay, that's all. Thank you very much.